43 billion miles from Earth. A machine older than most of your parents just picked up something that physics says shouldn't be there. Not a signal, not a ship, something stranger. A sound coming from the empty space between the stars. A sound that keeps getting louder the farther this spacecraft travels, when every single model scientists have ever built said it should be getting quieter instead. NASA doesn't have a full explanation yet, and the machine responsible for this discovery is Voyager 1, a probe built in the 1970s, running on technology weaker than a modern calculator, still transmitting data from a place no human instrument has ever been. What it just detected is rewriting what we thought we knew about the space beyond our solar system. Voyager 1 launched on September 5th, 1977, just a few days after its twin, Voyager 2. Voyager 1 launched on September 5th, 1977, just a few days after its twin, Voyager 2. Both spacecraft carried something remarkable bolted to their sides, a golden phonograph record assembled under the direction of astronomer Carl Sagan, containing photographs, natural sounds, music, and greetings in dozens of languages, meant as a kind of cosmic message in a bottle in case either probe was ever discovered by another civilization someday. At the time, that idea felt more like poetry than practical science. Almost 5 decades later, both spacecraft are still out there, still carrying that record, still drifting farther from home with every passing second. Both spacecraft were originally designed for a 5-year mission, a relatively short tour past Jupiter and Saturn, taking advantage of a rare planetary alignment that only happens once every 176 years. Nobody involved in that mission expected these machines to still be operating today, nearly 5 decades later. Nobody involved in that mission expected these machines to still be operating today, nearly 5 decades later. Along the way, before either spacecraft ever reached interstellar space, they rewrote what we knew about the outer planets entirely. Voyager 1 gave humanity our first close-up look at Jupiter's moon, Io, revealing it to be violently volcanic, nothing like the cold, dead moon most scientists expected. It also captured stunning detail of Saturn's largest moon, Titan, showing a thick, hazy nitrogen, rich atmosphere unlike anything else in the solar system. Those discoveries alone would have made the mission a historic success, even if the spacecraft had gone silent the moment its planetary flybys ended. Instead, it just kept going. And yet Voyager 1 is still out there, still transmitting, still traveling faster than any human-made object in history, currently moving away from us at over 38,000 miles per hour. In 2012, Voyager 1 did something no spacecraft had ever done before. It crossed the heliopause, the outer boundary of our sun's influence, and it became the first human-made object to officially enter interstellar space, the vast region between star systems. This wasn't like crossing a border on a map. The heliopause is where the constant outward stream of charged particles from our sun, called the solar wind, finally gets overpowered by the pressure of the interstellar medium beyond it. Past that boundary, you're no longer inside the sun's bubble. You're floating in the same material that fills the gaps between every star in the galaxy. Past that boundary, you're no longer inside the sun's bubble. You're floating in the same material that fills the gaps between every star in the galaxy. To get a sense of scale here, the heliosphere, the entire bubble carved out by our sun's influence, is absolutely massive, stretching many billions of miles in every direction. It took Voyager 1 tour d'espace, 35 years of continuous travel, moving faster than almost anything humans have ever built, just to reach its outer edge. That alone should give you some sense of just how enormous and how comparatively unexplored the boundary of our own solar system actually is. Scientists expected this crossing to answer a lot of long-standing questions. Instead, it opened up entirely new ones. The transition itself turned out to be far messier and more complicated than anyone predicted. One of the first surprises involved the magnetic field. Researchers assumed that once Voyager 1 crossed into true interstellar space, the direction of the surrounding magnetic field would shift noticeably, since it would no longer be shaped by the sun's influence. Instead, the magnetic field barely changed direction at all. It was a small but genuinely strange result, hinting that the relationship between our solar system and the interstellar medium around it was far more tangled than existing models assumed. That was just the beginning. The bigger surprise, the one still puzzling scientists today, has to do with something called plasma density. Interstellar space is often described as empty, but that's not entirely accurate. It's filled with an extremely thin, electrically charged gas called plasma, made up of loose electrons and ions drifting through the vacuum. This plasma is incredibly sparse, but it's not nothing, and Voyager 1 has spent the last decade plus quietly measuring exactly how much of it surrounds the spacecraft as it moves farther and farther from home. This plasma is incredibly sparse, but it's not nothing. And Voyager 1 has spent the last decade plus quietly measuring exactly how much of it surrounds the spacecraft as it moves farther and farther from home. To put the scale of this emptiness in perspective, The plasma out in interstellar space is almost unimaginably thin, often just a fraction of a single electron per cubic centimeter. For comparison, the air you're breathing right now contains something like 10 to the power of 19 molecules in that same tiny volume. Interstellar plasma isn't just sparse. It exists at a level of emptiness that's genuinely difficult for the human mind to properly picture, which is exactly why detecting subtle changes in it is such a delicate, painstaking process. Here's where things get genuinely strange. Based on standard models of the interstellar medium, scientists expected plasma density to either stay roughly constant or gradually decrease the farther Voyager traveled from the heliopause. Instead, the data showed the opposite. Electron density around Voyager 1 started climbing sharply beginning in 2013, and by around 2015, it had reached a level roughly 40 times higher than what the spacecraft first measured just after crossing into interstellar space. 40 times. That is not a subtle shift. That is the kind of number that makes scientists go back and question their assumptions from the ground up. If you're finding this as strange and fascinating as I do, go ahead and hit that like button. It genuinely helps this video reach more curious minds like yours. For years, measuring this density reliably was extremely difficult. Voyager 1 doesn't carry a dedicated density sensor built for this kind of long-range, continuous monitoring. Scientists relied on something called plasma oscillation events, brief bursts of activity triggered when shock waves from solar flares, originating back near our own sun, eventually rippled outward and slammed into the surrounding interstellar plasma, months or even years later. When that happened, Voyager's instruments would pick up a brief, musical-sounding whistle, and researchers could calculate the plasma's density based on the pitch and characteristics of that signal. When that happened, Voyager's instruments would pick up a brief, musical-sounding whistle, and researchers could calculate the plasma's density based on the pitch and characteristics of that signal. The very first time this happened, back in November of 2012, just months after Voyager 1 had crossed into interstellar space, scientists got their first ever confirmed audio evidence that the spacecraft had truly left the heliosphere behind. Then, 6 months later, a second whistle arrived, this time noticeably louder and higher pitched than the first. Even from those two early data points alone, it was already becoming clear that whatever region Voyager 1 was now traveling through, it appeared to be getting thicker, and doing so surprisingly quickly. The problem was, these events were rare, happening only about once a year, which left huge, frustrating gaps in the data. Then, in 2017, something changed. Voyager 1's instruments began detecting a completely different kind of signal, a faint narrowband. That wasn't tied to any solar event at all. Unlike the sudden, dramatic whistles triggered by solar shock waves, this new signal was quiet, persistent, and continuous, almost like discovering a constant background frequency nobody knew was playing the entire time. Stella Ocker, a researcher at Cornell University who led the study analyzing this discovery, described it as offering a genuinely new way to measure the density of interstellar space, opening up an entirely new path for studying the structure of the region immediately surrounding our solar system. This was a big deal for one simple reason. It meant scientists no longer had to wait around for rare solar shock waves to get a snapshot of the plasma density. Voyager 1 was now essentially humming a continuous, steady note that researchers could track in real time, regardless of what the sun happened to be doing at any given moment. Shami Chatterjee, a research scientist at Cornell, involved in the work, explained it simply. He said that regardless of what the sun is doing, Voyager keeps sending back detail, essentially reporting back the exact density it's currently moving through, over and over, continuously, as it drifts farther into the dark. So what's actually causing this unexpected density increase? Scientists have proposed a few possible explanations, though none of them are fully confirmed yet. One leading idea involves the shape and structure of the local interstellar medium itself, the specific patch of space our solar system happens to be passing through right now. Some researchers believe our sun is currently moving through an unusually thin, hot region of interstellar gas, and that Voyager 1 may now be approaching the edge of that region, entering denser material that was always out there, just farther away than anyone initially anticipated. Another possibility involves the heliopause boundary itself, acting almost like a kind of pressure wall, compressing and altering the plasma density in the region immediately surrounding it, an effect that could gradually fade the farther Voyager travels beyond it. There's also ongoing research into interstellar turbulence, essentially small-scale chaotic fluctuations in density and magnetic fields that ripple through the interstellar medium, which could be creating localized pockets of denser plasma that Voyager happens to be passing directly through right now, rather than reflecting some larger galaxy-spanning trend. To be completely clear here, because this is important, none of this involves anything resembling contact, signals, or communication from an outside intelligence. This is not that kind of story, and it's worth saying plainly. What Voyager 1 detected is a natural physical phenomenon, plasma oscillations, the same basic physics behind auroras here on Earth or the solar wind itself, just occurring in a region of space no instrument had ever directly sampled before. The reason this keeps making headlines isn't because it's spooky. It's because it's genuinely unresolved science, real data that doesn't yet fit neatly into our existing models. There's something worth pointing out about the sound itself too, since NASA actually converted this plasma wave data into audible frequencies that humans can listen to. What you hear is not a voice, not a message, and not anything resembling language or intention. It's a faint, eerie, almost musical tone, generated by electrons vibrating at specific frequencies as they interact with the surrounding plasma. Scientists sometimes describe it as the background hum of interstellar space itself, a sound that's technically been playing out there this entire time, completely inaudible, until a 50-year-old spacecraft happened to be in the right place to finally pick it up. Researchers have been careful to separate genuine scientific mystery from online speculation here, and for good reason. Whenever a story like this breaks, a certain corner of the internet immediately jumps to theories involving alien contact or hidden signals. Scientists studying this data have been fairly blunt about that possibility, noting there is currently no evidence whatsoever supporting anything like an artificial or extraterrestrial signal buried in Voyager's readings. What they have found is something arguably more interesting from a scientific standpoint, a real physical anomaly in the density structure of the space surrounding our solar system, one that existing models simply didn't predict. It's worth remembering just how remarkable it is that we're getting this data at all. Voyager 1 is now more than 15 billion miles from Earth, so far away that a radio signal traveling at the speed of light takes over 22 hours just to reach it, and another 22 hours for any response to make its way back to mission control. That means every single command sent to Voyager 1, and every scrap of data it sends home involves a round-trip communication delay of nearly 2 full days. Troubleshooting any issue on a spacecraft. This distant isn't like fixing a glitch on your phone. It's closer to sending a letter into deep space and waiting patiently for a reply that takes the better part of 2 days to arrive. And Voyager 1 is not in great shape these days either. Both Voyager probes run on radioisotope thermoelectric generators, devices that convert the heat from slowly decaying plutonium into usable electricity. Both Voyager probes run on radioisotope. Thermoelectric generators, devices that convert the heat from slowly decaying plutonium into usable electricity. Unlike solar panels, which become essentially useless this far from the sun, where sunlight is thousands of times weaker than it is on Earth, these generators don't depend on sunlight at all. They work by harnessing the natural heat, released as plutonium-238 steadily decays over time, converting that heat directly into electrical power through a solid-state process with no moving parts to wear out. It's an elegant, remarkably durable design, exactly the kind of engineering choice that made a 5-decade mission even remotely possible in the first place. The power source has been steadily weakening year after year since launch, forcing NASA engineers to make difficult decisions about which instruments to keep running and which ones to power down permanently, just to keep the spacecraft alive a little longer. Multiple instruments have already been shut off over the years, specifically to conserve what little power remains. Every year that passes brings the mission closer to its inevitable end, which makes every new piece of data Voyager sends back feel a little more precious than the last. If this kind of deep space mystery is exactly the type of content you love, make sure you're subscribed, because there's a lot more of this coming and you won't want to miss it. Despite its age and its fading power supply, Voyager 1 remains genuinely irreplaceable, and that's not an exaggeration. No other spacecraft in human history has ever traveled this far, and none currently in operation are anywhere close to reaching interstellar space themselves. Voyager 2, its twin, also crossed the heliopause back in 2018 and has provided valuable comparison, data from a slightly different direction. But Voyager 1 remains our deepest, most distant window into this completely unexplored region of the galaxy. Every single measurement it sends back is, by definition, something no human instrument has ever recorded before, since nothing else has ever physically been out there to record it. Voyager 2, its twin, also crossed the heliopause back in 2018 and has provided valuable comparison data from a slightly different direction, but Voyager 1 remains our deepest, most distant window into this completely unexplored region of the galaxy. Interestingly, Voyager 2 crossed into interstellar space at a noticeably different location than its twin, giving scientists 2 separate vantage points on this boundary rather than just one. Early comparisons between the two spacecraft have already revealed that the heliopause isn't a perfectly smooth, symmetrical bubble, the way earlier models tended to assume. It appears to be uneven, possibly even somewhat lumpy in shape, shaped by pressures and magnetic forces that vary, depending on exactly where you cross it, adding yet another layer of complexity to a boundary that already refuses to behave the way anyone predicted. That's precisely why this plasma density anomaly matters so much, even without a confirmed explanation yet. It's not just an interesting curiosity. It could fundamentally reshape how scientists model the structure of the space immediately, surrounding our solar system, which in turn affects everything from theories about how our sun moves through the galaxy to practical calculations about radiation exposure and hazards that future interstellar missions would need to plan around. Understanding the true density and structure of this boundary region isn't just an academic exercise. It's essential groundwork for any future spacecraft that might eventually follow in Voyager's path. There's also a broader scientific lesson buried in all of this, one that goes beyond plasma physics specifically. Voyager 1 was built using technology from the mid-1970s. Its onboard computer has less processing power than a basic modern digital watch. And yet, decades after launch, it's still managing to challenge and refine cutting-edge theoretical models developed by scientists who, in most cases, weren't even born when the spacecraft first left Earth. That's an extraordinary testament to careful engineering, but it's also a reminder that sometimes the most valuable scientific data doesn't come from the newest, flashiest instrument. Sometimes it comes from something old, persistent, and simply present in a place nothing else has ever managed to reach. NASA's Voyager team continues to closely monitor this rising density trend, along with the rest of Voyager 1's slowly aging instrument suite, hoping to gather as much continuous data as possible before the spacecraft's power finally runs out for good, an event current projections suggest could happen sometime around the end of this decade. Every additional year of operation adds more data points to this unfolding density mystery, giving researchers a better chance of eventually identifying exactly what's driving the change, whether that turns out to be a broader structural feature of the local interstellar medium, some kind of localized turbulence, or possibly something about the physics out there that nobody has fully considered yet. For now, the honest answer is that scientists don't fully know why interstellar space appears to be getting denser exactly where Voyager 1 happens to be traveling through it. What they do know is that a machine built nearly 50 years ago, running on power levels a modern smartphone would consider laughably weak, continues to detect real, measurable physical phenomena that our best current models simply failed to predict. That's not a glitch. That's not aging hardware malfunctioning. That's a genuine scientific mystery unfolding in real time over 43 billion miles away from the place where it all began. Somewhere out there, beyond the reach of our sun's influence, a 50-year-old machine keeps sending back a quiet, steady hum from a region of space no human being has ever physically visited. It doesn't carry a message. It isn't trying to tell us anything intentional. But in its own strange, accidental way, it's still teaching us more about the universe than almost anything else humanity has ever built. And as long as its power holds out, Voyager 1 will keep listening to a sound scientists still can't fully explain, quietly rewriting the edges of what we thought we understood about the space beyond our own solar system. 50 years after leaving Earth, carrying nothing but a golden record and a handful of aging instruments, this small machine is still finding ways to surprise the very scientists who built it. And there's something quietly remarkable about that. A reminder that even our oldest tools can still lead us somewhere entirely new.